Good morning. So my name is Sophie Valcke, and I will give this webinar organized by IS-ENES3, the European project, on the code coupling. So I will give an overview of general concepts on code coupling and then the latest news of the OASIS3-MCT coupler. So this is the outline of my talk. I will start with the general introduction. And then in the first part of the webinar, I will discuss global performance and technical solutions, insisting on the difference between sequential versus concurrent coupling and trying to categorize different coupling software into two big families, the integrated coupling framework approach versus what I call the external coupler approach. In the second part, I will describe few coupling software. So the Earth System Modeling Framework, ESMF, the NRCAR coupling framework, CPL7, the Flexible Modeling System, FMS, and then I will spend more time on the coupler that we developed at CERFACS that is funded by IS-ENES3, OASIS3-MCT. And then in the third part of the webinar, I will provide more detail on the latest development that were included in the latest release of the coupler, OASIS3-MCT 5.0 in December. And then I will conclude and give some perspective. So first, as a general introduction, so why do we want to couple ocean, atmosphere, land, sea ice models? Of course, it's because we want to model the Earth system globally, and we want to model not only the components themselves, but also their interactions and their retroactions. So what does coupling of codes imply? So when you couple codes, of course, the first task is to exchange information at the code interface and transform it. For example, to run, the atmosphere needs as a boundary condition the sea surface temperature that is calculated, provided by the ocean. So you need to transfer this information, the sea surface temperature from the ocean to the atmosphere, and you need to transform it from the grid of the source model, the ocean, to the grid of the target model, the atmosphere. And of course, you need to do this in a synchronized way. And that's why the coupling codes also involves managing the execution and the synchronization of the codes. So what are the constraints? Of course, you would like coupling to be easy to implement, flexible, efficient, portable. The coupling algorithm, that is the way you exchange the coupling field, is of course dictated by the science that you want to model. So you have to respect this. A big constraint is that usually you start from existing models that have been developed independently by independent groups. And of course, you want the global performance and the load balancing of your couple model to be as good as possible. And you have to take care about the characteristics of the computing platform that you are running on. So for the first part on global performance and technical solution, let me introduce. When you start implementing a couple model, you have to ask yourself how you want to use the computing resources you have at hand, so to optimize the performance of your coupled system. But optimizing the performance of a coupled system can have different meaning. Do you want to optimize the throughput of your couple model in terms of simulated years per day? That is, do you want to get the result as fast as possible? Or do you want to optimize the use of resources in terms of simulated years per CPU hours? That means make the best use of the resources you have. And whether you ask yes to one of these two questions or the other, you will not necessarily lay out your component the same way on the computing resources. So that's what I'm saying. How do you use your computing resources? That is how you run your different components of your couple model on the computing resources you have. And a big question to ask, important question to ask is your coupling sequential or concurrent or a mix of both? And I will give more detail about that. When I speak about sequential coupling, I mean that, and this is illustrated here on the top left, it means that you have, this is an example of two components running, and you see that time is going from left to right. And you see that when the first component is running, the other cannot run, and vice versa. So sequential coupling means that you have really one component running, delivering a coupling field to the second component that then can start, and then the second component delivers a coupling field to the first component that can resume. This is, for example, the case when you have the, if you want to solve the heat diffusion equation from the top of the atmosphere to the bottom of the land. When you write this equation and when you discretize it, you end up with a tri-diagonal system, and you have to solve the coefficient of the matrix. And you did this by a down and up sweep. This is quite classic in numerics. And then you do this, when you do this in the atmosphere, you're not doing this in the land and vice versa. So if you have that type of coupling, what you want to do is you want to run all your components sequentially, that is one after the other, on the computing resources you have. This is illustrated here on the bottom left. You have the first, you see the time is going from up to down, and you have horizontally, you have the different computing resources. And you see that all the resources, the 5 cores here, are first used to run the first component, and then the second component, and then again the first component. So that's how you want to use your resources if you really want to implement a sequential coupling. So the advantage of this type of coupling is that as you are running your component on the same set of cores, you can implement efficiently the coupling exchange through memory exchanges because you are sharing the memory. It's quite good for load balancing because you are using all your resources all the time, but it also means that a constraint is that you are running your component on the same number of cores, so they have to be efficient on that number of cores. If you do that, then it means that you put all your components into one big program, into one executable, and you may have some conflicts doing this. And another drawback is that you have no flexibility in the coupling exchanges, because the only thing you can do is run the component, transfer the field to the second one, run the second one, and then transfer back some coupling fields from component 2 to component 1. So there's no what we call in-place exchanges. So this is a type of coupling. The second type of coupling that you may want to implement is concurrent coupling. And in that type of coupling, the two components are running at the same time on different sets of resources, and they exchange the coupling field either at the end of the coupling time step or even during the coupling period. That's traditionally how we implement ocean-atmosphere coupling. When you want to implement that type of coupling, what you want to do is that you want to run one component on a subset of your resources. For example, here you're running component 1 on core 1, 2, 3, and then you want to implement to run your other component concurrently in parallel on another set of computing resources. This is illustrated here. And so the advantage of this type of implementing the coupling is that you have an additional level of parallelism. The components themselves can be parallel, but then you also run them in parallel. So you have this additional level of parallelism in the coupling. The coupling algorithm itself can be more flexible than in the previous case, because as the components are running at the same time on different sets of resources, you can implement the coupling exchange whenever you want during when they run. When you implement that type of coupling, you can either decide to assemble the two components into one executable, but if you do this, you may have possible conflicts, or you can run them as separate executables. It might be less efficient than in the previous case, because here you probably have your components running on different sets of cores, and you cannot use the memory to exchange the coupling fields. And you have to take care about the load balancing, because in this case, you have to find the number of cores so that component 1 and component 2 run at the same time. You don't want one component to run faster than the other, because it means that it would wait for the other component, and then you would waste resources. So this is this is, I mean, very this is a very schematic view of the coupling, either sequential or concurrent. And in practice, of course, in many cases, you implement a mix of those two. So in practice, what are the technical solutions to implement your coupling? So the first thing you can do, and that's what they do, for example, at ECMWF, you may not use any tool, any software, any coupling software. You just transform one of your component in a subroutine, and you have the other component here, prog1, which calls the second component as a subroutine. And you transfer the coupling fields as argument when calling the subroutine. If you do this, well, this can be quite efficient, because again, you can exchange the coupling field through the memory. It's of course as portable as the codes themselves are. You end up, when you do this, your coupled system end up being in one big program, one big executable, and it might be easier to debug and easier to manage for the operating system. And this is, of course, very good if you want to implement sequential execution of your component, because you run first, a part of prog1, then you run your prog2, and then again, you run the rest of prog1. So this is typically a sequential execution of the component. But the drawback is that it might not be that easy to implement with existing codes, because of the merging. It's not really flexible regarding the coupling algorithm, because the only thing you can do here is exchange the coupling field through the arguments here. And of course, as you are not using any generic coupling library, you have to write your own transformation and interpolation. But still, some people decide to do that. That's how coupling is implemented at ECMWF between IFS, which calls NEMO as a subroutine. So it is a technical possibility. The second approach, which is quite used in the States, is what I call the integrated coupling framework approach.
Sophie, about 2 minutes.
Okay, great, that's fine. You start with your original programs, so prog1, prog2 here, and you split them into elementary units, and then you adapt the data structure and the calling interface of those units, and then you use the framework to rebuild, you rewrite a new hierarchical merge code. And this is typically what is done with ESMF that I will present after. And you see that when you rebuild your new code, you can decide to run your units either concurrently at the same time on different sets of resources, or one after the other on the same resources. So this can be quite efficient. As I said, sequential and concurrent components are supported, and you can of course use all the utilities that come with the framework. But the drawback is that it's not that easy to implement with existing codes, because you have to split them into elementary units to adapt the data structure and calling interface. But still, I think this is probably the best solution in a controlled development environment. That is, if you can agree between all the people developing the models that you agree to use the same standard, the same coding standards, and the same framework. Now, the third approach that you can use, and this is what we do with the OASIS coupler, is to use an external coupler or coupling library. And here, the philosophy is very different. You change your program, your original program, as little as possible. You just implement some routines to send or to receive the fields, and you link your components, your programs, with the coupler, with the coupling library. That takes care of the coupling exchanges based on a configuration that the user writes externally. So here you see that the difference between the two approaches are really different. The big advantage of the coupler or external coupling library approach is that it's easy to implement with existing codes because you change the code as little as possible. It's, of course, very well adapted to concurrent coupling because you leave your original program, you keep them, you let them run concurrently at the same time, and you just exchange a coupling field within the time step. But it may be, of course, less efficient because you have to use, for example, message passing to exchange a coupling field. You cannot use the memory. And you end up with more than one executable, which might be more difficult to debug. But still, I think that it's probably the best solution to couple codes that have been developed independently and for which it would be hard to impose a standard framework. So just to finish, this gives you an illustration of the different coupling software that are used in Earth system modeling. This is the time at the bottom going from 1990, the year 1990 to today. And you see that OASIS has been developed for more than 20 years now. I mean, the coupler, at the top you have the software which adopt the approach, the external coupler or external coupling library approach. You have here, so OASIS3-MCT, as you said. You have also the first version of the NRCAR coupler. You have DDB, which is developed at UCLA. You have the MCT coupler, the C coupler developed in China. You have Valcke, which is developed in Germany. And more recently, you have Moab Tempest Remap developed in the States. And for the software that followed the integrated coupling framework approach, you have FMS, ESMF, and CPL7. And in the next section, I will describe in more detail these three software and of course, OASIS3-MCT. Okay, so just as a summary, in the first part, I tried to stress the fact that when you are assembling a coupled system, you have to take care about, I mean, the coupling algorithm, the way you want to exchange your coupling field, the way you want to run your components, influence the way you will use your computing resources. And you have to think about that, so to have a performance system. And then I presented, I think that we can split the different coupling software that exists into two main categories, as I said, the external, and those are two ways of assembling a coupled system for which the philosophy is very different. In the integrated coupling framework, you rewrite a new integrated code. With the external coupler or coupling library approach, you transform your code as little as possible, and you use an external library. So this is very different philosophy. Now, in the second part, I will present in more detail few coupling software. So let's start with ESMF. ESMF is the Earth System Modeling Framework. It's an open source software for building earth science application. It's based on components, of course, developed in different modeling centers. It's funded by different agencies in the States. Today, we have at least 37 different components that is a model, for example, an ocean or an atmosphere or a land model that have been adapted to the ESMF new OPSI standards. And this is the number of components listed, but we have probably much more than that that are not declared. ESMF, as most coupling software, offers what they call an infrastructure. Those are tools that you can use internally in your code, in your component, for example, to manage the time or to parallelize your code. And then you have what they call a superstructure, which is really the standard interface that you have to wrap your component in so that they can interact with other ESMF new OPSI components. This is an illustration of the Goddard Space Flight Center GEOS 5 model that has been completely rewritten or written or reassembled with ESMF. And you see here that they have, I mean, it's one big code into which the original components, for example, you see here the atmosphere, or you see here a lake component. So you see that all the components have been merged into one big executable, and all these components, they have their interface has been adapted. They all adhere to the ESMF standards, and that's how you can rebuild a new code with those components. So what a component has a well-defined function, and it has a calling interface which is adapted to ESM, which uses the ESMF standards. They have two types of components, a gridded components that really contain the scientific code, and a coupler component for everything that regards transfer and data transformation. And as I said, the user builds with ESMF, the user builds a new model as a hierarchy of components. And in this new executable, the components can be run sequentially, concurrently, or in a mixed mode. So this follows what I call the integrated coupling framework approach. Everything is reassembled into one big executable. And it's important to mention that there is the new OPSI layer, which is, I mean, with the ESMF originally, the user has to rewrite the new code, but new OPSI offers convention and templates so that can be reused so to recreate a specific coupled models. Now for the NRCAR, for CPL7, the NRCAR coupler, this is a top. CPL7 is really a driver. It's a top level layer that calls the different components. They have a coupler components, but they have also an atmosphere, ocean, land, and sea ice. And the different components can be called in sequence or in parallel. It's developed by the NRCAR Earth System Laboratory, and it's used in the CMIP6 models at NRCAR. And it's interesting to note that NRCAR went from the coupler approach. CPL6 was really following the coupler approach to the integrated coupling framework approach with CPL7. And it uses MCT internally with ESMF, and it also supports ESMF compliant components. So without going into the details, CPL7 is really a driver that launches the different components and that prepares whatever is needed to run those components. And here is just an illustration of the different layouts that you can have. We have 3 different layouts. And the user can choose the layouts just by an external specification. So you see here at the left, all the components are run one after the other on all the computing resources. But you can also have a layout here, for example, at the middle where the ocean is run concurrently with the land and the ice and part of the atmosphere. But we see here that with this layout, there's some load imbalance. And then you also can run even here this layout on the right, which is even more parallel because here you have the ice, the land, and the ocean. And what is really nice with CAPR7 is that depending on the characteristics of your components, your resolution, the platform you run on, you can switch from one layout to the other easily just with an external specification. Now for FMS. FMS is developed at GFDL for more than a decade now. It's been used for CMIP6 again. It's been shown to be quite scalable. And as ESMF, it offers what they call an infrastructure and a superstructure. I think the idea when ESMF started were really taken from EFMS. So the infrastructure is all the tools that FMS offers for the component itself internally, for example, to manage the I/O or for managing the parallelization of the component itself. And it offers a superstructure. That is like ESMF standard interface that you have to adapt your component to build a single executable coupled model. What is nice about FMS is that it allows an implicit calculation of the vertical diffusive flux over the whole column. As I presented earlier, this is the diffusion equation, and you can solve this from the top of the atmosphere to the land, even if the atmosphere and the land do not share the same grid. And to do this, they define the concept of an exchange grid. The exchange grid is the intersection of for example, here in this case, the atmosphere and the land model. And FMS allows, for example, this implicit calculation of the vertical fluxes across the two components going through the exchange grid. So doing the regridding of the fields. Okay, so this is a quick overview of 3 different coupling software that follow the integrated framework approach. And now I will present in more detail the OASIS coupler that is developed by CERFACS and by CNRS with funding recently by IS-ENES and also EasyWays. So OASIS3-MCT has been developed for more than 20 years now. We started in 1991 with the series of OASIS1, OASIS2, OASIS3. This was not parallel. And when at the time, the idea was to insist on flexibility. And then in 2001, when the PRISM project started, we were faced with a higher resolution model that were themselves parallel. So we started developing a parallel coupler, OASIS4, which was used in a few coupled systems. But then at one point, we decided to stop the development of OASIS4. And this is when we interface MCT, the model coupling toolkit, in OASIS3-MCT. And that was quite successful because we had no real change in the API, in the application programming interface. So it was quite transparent for the users themselves. And just by changing the library, they had a parallel coupler. We had now the last version was released in December, and it's OASIS3-MCT 5.0. And I will give more detail about this version in the third section of the webinar. So in 2019, we did a survey, and we concluded that it was at the time, so it's probably even more today. OASIS3-MCT is used by at least 67 climate modeling groups all around the world to assemble more than 80 coupled applications. OASIS3-MCT is used in 5 of the 7 European ESMs in CMIP6. So we have a very large community all over the world. So just some generalities. Everything is written in Fortran 90 and C. As I said, it uses the model coupling toolkit from Argonne National Lab as a lower layer to manage the communication, the exchange of the coupling fields. Everything is released under an LGPL license, and it uses, all the library it uses are either public domain or open source. Currently, the permanent developers are CERFACS and CNRS. So we have a commitment of about one person full-time. And we're also working with two consultants, Anthony Cray and Andrea Piacentini. And it's interesting to note that Anthony Cray is the developer who developed CPL7, and he's also involved in the development of ECMF. So as I said, in the few, let's say 4 years, OASIS3-MCT development has been funded by IS-ENES and by EasyWays, the Center of Excellence. So just to give you a flavor of what it means, and you have here, by understanding this, you can really understand what it means, this coupler approach. The idea is that you don't have, you keep your code as it is, and you just have to implement some calls to do the coupling in your code. So you first have some initialization call, OASIS init comp, and then this is a very important one, the local partition definition. Each process will call this OASIS def partition to describe the local partition of the coupling field that it will send or receive. And that's how the coupling library OASIS can do the redistribution of the coupling data between the different components. And then you have to implement a call to describe your grid. You have to declare the coupling field with an OASIS def var, and then you close the definition phase. The first part was the initialization phase, and then in the model time stepping loop, you have to implement OASIS put to send some data or OASIS get to receive some data. And you see here that as argument, you have a date, which means which has to be the time at which the put or the get is done, is valid. And you have an array that either contains the field that will be sent or the field that will be received. But beside those arguments, you have nothing specific. For example, in the OASIS put, you don't have to specify the target, where it will go. For the OASIS get, you don't have to specify where the data will come from, where the coupling field will come from. This is defined externally by the user in a configuration file. And this means that it's quite convenient. It means that if you implement these calls quite in a generic way, you don't have to change your code when you change your coupled model. So we have few models that have implemented these calls in a generic way. We have NEMO, we have WARF, we have OpenIFS now. They have these generic interface, and means that when someone uses those models, wants to build a coupled model based on those models, on those components, they don't have to go in the code. Everything can be specified externally. You also see that, for example, the coupling frequency is not specified in the put. So basically, in the model, you can call the put or the get every time step, and the date will be analyzed, and the coupling exchange will be done if it's a date that corresponds to a coupling period as specified in the external configuration file. So this is, again, very convenient. If you want to change your coupling frequency, you don't have to change your code. You just change your external configuration. And then you have a termination call. Now, OASIS, with OASIS3-MCT, you can ask the coupler to perform some interpolation and some transformations on the coupling fields. The fields that are supported are 2D or 3D scalar fields, and we also have bundles. For example, if you have different categories of ICE, you don't have to define one coupling field per category of ICE. You define just a bundle, and it's easier to manage. Almost all types of grids that are used in Earth system models are supported. We have some transformation. For example, you can do some statistics. You can do some addition, multiplication by a scalar. We also have this global conservation transformation, which forces the conservation of the coupling field if ever the regridding or the interpolation is not conservative. Then regarding the interpolation and the regridding, this is, I mean, traditionally we do this online with the script library, and you have here the reference, the Jones paper. But now what is new in OASIS3-MCT 5.0 is that we offer a unified regrid environment that is just, you know, a setup so that you can easily calculate your regridding weights with either script, ESMF, or XIOS. So you can even, because we were not that happy with the script library, especially near the poles. And so that's why we started looking at other libraries to do the regridding. So you're not using ESMF or XIOS to do the coupling per se, but you can use ESMF or XIOS to calculate your interpolation or your regridding weights. So you can, for example, do a nearest neighbor. So this means that for each for each grid point of the target grid, you will use the closest point on the source grid. You can have a bilinear algorithm. So for each target point, you use the 4 enclosing neighbors. You can use even a higher order non-conservative, like a bicubic or a patch algorithm from ESMF. You can use a conservative remapping, for example, first order. In this case, for each, I mean, a target point is associated to a cell, to a target cell, and the source cell that contributes to the calculation of the grid point on that target cell are the cells that are intersecting the target cell, and the weight is proportional to the area intersected. That's how the conservative remapping works. And you have first order or second order. And so I will talk a little bit more about this new functionality of calculating the weights with ESMF or XIOS and the work we did to benchmark those libraries in the third part.
About 2 minutes.
Okay, good. So regarding the parallel, the communication, so how the coupling fields are exchanged in OASIS3-MCT, well, the exchange is fully parallel, and as I said, it uses MCT, the model coupling toolkit, which uses message passing interface, MPI. So here you have an illustration of how coupling exchanges between two models. Model 1 here in this sketch runs on 3 processes. You see that each process treats a part of the coupling field, and basically each process just declares its part of the coupling field and sends its part of the coupling field, and it is the library, the OASIS3-MCT library based on MCT, that automatically calculates the redistribution patterns and performs the redistribution of the data to the target model. Those, as I said, you can interface, you can adapt your model very generically, and you can configure your coupling exchanges externally in the configuration file, which is called namcouple. That's where you specify the source and the target symbolic name. That's how you make the link between a field that is sent by one model to a field that another model wants to receive. That's where you specify the coupling, the exchange or the coupling period, and that's where you ask OASIS3-MCT to perform some specific transformation or interpolation. As I said, the weights, the interpolation regarding weights and addresses can be calculated either online with the script or offline with script, ESMF, or XIOS. And we also want to mention that we have an I/O functionality. That is, instead of sending a coupling field to another component, the component can write it to a file, or instead of receiving a coupling field from another component, it can read it from a file. So it means that you can use the OASIS interface to switch between the couple and the force mode. Now, regarding the possible topologies of the coupling exchanges, let me here we have an illustration, for example, of a first component, which I called here Atmos, which runs on 6 different processes, 6 MPI tasks. And this is one executable. So it has, in the OASIS jargon, it will define one component and it runs on one grid. Let's suppose that you want to couple this with a much more complex executable. This is illustrated here in blue. This second executable runs on 32 tasks. And you see that it defines different components running concurrently. For example, here you have component 2 running using a grid, which we call here grid 2. For example, it's an ice model. And at the same time, you have the ocean part. And at the same time, you have, for example, few tasks that are used that are not doing any coupling and that are used to perform input-output. And even within one component, you can define different grids. Part of the code will, for example, use grid 3, which runs at the same time, and on other processes running at the same time, they will do something on some fields on grid 4, and then afterwards, all the processes all these processes will be used to run something on even another grid. So if you have that type, if you have those type of components and you want, what are the coupling exchanges that you can implement? Well, you can implement standard coupling exchanges between concurrent executables. That's the very standard way. I mean, the components run in parallel and you implement coupling exchanges between this. This is a standard coupling exchanges of the external coupler approach. But with OASIS3-MCT 3.0 and 5.0 and 5.0, of course, you can even implement those type of couplings. That is, you can implement exchanges of coupling fields between 2 different components that would run within the same executable concurrently at the same time. Those are illustrated here in green. And you can even now implement coupling exchanges between sequential components within one executable. So this is possible with OASIS3-MCT. So this means that basically that by extending the functionality of OASIS3-MCT this way, we see that basically the OASIS3-MCT that I categorize in the coupler approach gets some characteristics of the integrated coupling framework approach. You know, with having different components running in sequence or concurrently within the same executable. So it's the 2 families of coupler that I describe. This is, let's say, a very first categorization, but in practice we see that coupling software that follow the coupler approach extend their functionality to have some characteristics of the integrated coupling framework approach and vice versa. For example, ESMF supports web services, which means that an ESMF component can in fact exchange some coupling field during the run with another component running at the same time somewhere on the internet through web services. So we see that both approaches try to, I mean, they start with a philosophy and then they try to extend their functionality so to get the advantages of the other approach. Okay, so now the last OASIS3-MCT 5.0 was released in December within the IS-ENES project. So regarding source management and training, we migrate from SVN to Git, and we kept the full history of the SVN repository, and that was very nice work done by Andrea Piacentini. We have now a new website. We migrate from the DKRZ website to a website which is hosted at CERFACS, and you are more than welcome to visit it. Within Easy Ways, we were funded to develop a short private online course, what we call a SPOC. And we are really pleased to have done this. We already had 3 sessions. We have up to now 20 participants. And we have overall very good feedback of this way of getting trained on OASIS. So we have, I do not mention this on the slide, but we have 2 types of SPOC. We have some official sessions where I'm available and the participants can interact. But we also have on-the-fly session. That means someone who would like to get trained with a SPOC without and cannot wait for the next official session. There's also a specific SPOC that you can work with. So this SPOC offers about 20. I mean, you as a participant, you have to plan to work for about 20 hours over. Well, 2 weeks when it's those are the official sessions, and it offers a mix of theory, videos, quizzes, and hands-on. You really do a practical work. The goal of the training is to instrument 2 toy models to set up a coupled model exchanging 1 field in each direction. And so when you end up the SPOC, you really have done the instrumentation, and basically you basically know what you have to do in your couple model. And then there's a section on regridding or interpolation. So regarding tools and interface, we now have a new Python. We have new Python, C and C++ bindings, and it's already been used at SMHI to set up a standalone regridding weight computational tool. And we are looking for more users. So if you have a Python or a C component, then you are now able to couple it to other components with OASIS3-MCT. We have a new load balancing tool, which is the evolution of the Lucia tool that was developed by Eric Maisonneuve through a collaboration with BSC, with the Barcelona Supercomputing Center. So this interaction, this cooperation led to this new load balancing tool, which is much more evolved than what we had with the Lucia tool. This tool gives you a graphic view of all the coupling actions that are realized in a coupled system. You have here, for example, the time going from left to right, and on the y-axis you have the different processes used by either the I/O server or here the atmosphere or the ocean. And for example, this gives you a very right away you can see, for example, the time where the atmosphere is, for example, waiting for a get in orange here in this case, or vice versa, the ocean. And if you ask a question, we don't see the put because in blue, because they are, the put is not blocking. So there are some blue lines here, but we would have to zoom to see the blue lines of the put. But this new tool is very powerful to help you load balance your system and make sure that you run an efficient coupled system, as I was describing in the first part of this webinar. Now, regarding regridding, or we call regridding interpolation or remapping, just first I want to mention that we have an extension of the OASIS Get Intracom so that now for a couple model involving XIOS that manages ensemble simulation. So this is used now at IPSL and at the Met Office or at NCAS. I'm not sure, at NCAS, I think. We have also, Eric Maisonneuve developed a new locally conservative remapping, which is especially needed for runoff. Runoff, when you want to couple the runoff, it's very specific because you want a conservative remapping, but you have no surface intersection usually between the river outlet and the ocean cells where you want the runoff to be delivered. And also what you want to make sure in that case is that every source point, that is every outlet, the water of every outlet point gets somewhere in the ocean. Usually that's the opposite that we want. We want to make sure that for each target point of the target grid, we have some value. So this interpolation, this remapping of the runoff is very specific, and we now have something that does this automatically. And as I said, we have this new environment to calculate the regridding weights offline with either the script ESMF or XIOS. So you can pre-calculate your weights and you can check the quality of your remapping, and you can choose the one you prefer. And to do that, we had the first step where we performed an extensive benchmark of the regridding functionality of script, ESMF, XIOS, and YAC. YAC was included in this benchmarking. And basically, it's just a question of time. I mean, at one point, we would certainly include YAC also in this unified environment because it offers also some very good remapping. So we you have here two references, either a technical report where you have all the results of this benchmarking. We analyze 5 different regridding algorithms, including first and second order conservative or non-conservative algorithm. We analyze the results for coupling fields defined by 4 different analytical functions. And we used 6 grids used in real ocean or atmosphere model, and we performed the calculation proposed by the Kanga project. And you have here just an illustration. For example, this gives you the global conservation for different here at the on the x-axis. Those are different couples of grids. Of course, those are grids acronym, and you see the results for the different libraries. ESMF script with 2 different options, YAC in pink and XIOS in black. And so we have analyzed, we have those types of graph for 5 algorithms, 4 different analytical functions, and all the couples of grid and all the these remapping library. So it's quite an extensive analysis of the regridding possibilities that you can use for Earth system modeling today. This gives you just an illustration of this, the work we did. You have here, for example, the error. We defined this function, the vortex function, which has a like kind of a vortex, 2 vortices, and you have here the error for the first order conservative mapping, and at the bottom for the second order conservative mapping. This graph is from YAC, but we got similar results for the other libraries, and we see here that the second order remapping, conservative remapping, is much better. It reduces the error because it reproduces the gradients of the function. So this is the type of analysis we did in this work. And then we also did the first analysis of the performance of script, ESMF, and XIOS, and this gives you the time to calculate the regridding weights when going from the ORCA 12 grid, which has about 13 million of points, to a high resolution version of a high icosahedral grid with 2 million of points. And the x-axis is when you increase the number of cores used for the weight calculation. And we see that ESMF and XIOS are much more performant than the script. That's what we were looking for. We also see that at low number of cores, XIOS is more performant than ESMF, but it shows some unstable behavior at a higher number of cores. And we have to, this still has to be investigated. But the general conclusion is that with those new, let's say, new libraries, online regridding is really becoming an option, because you can imagine that if it takes not that much time to do the calculation of the weight, you can redo that during the run, and you can then support grids evolving in time, grids that evolve in time. Okay, so I guess I'm done. So I will just conclude. So as I said, in the first part of the talk, I talked about global performance and technical solution. I tried to insist on the importance of the layout of the components of the computing resources to get an efficient couple model. And I think that many people run their couple model without even really looking at that. And, you know, it runs, it's fine, but, you know, you have to, it's not an easy task, but you have to look at the results. You have, for example, to use the new load balancing tool to really see if one component is waiting for the other or not, to better load balance your system. And that's how you will be able to optimize your system. In that part, I also propose a first categorization of the different coupling software into two families that I call the integrated coupling framework approach, and the other, which I call the external coupler or coupling library. And then I described few coupling software. For the first category, I described ESMF, CPL7, and FMS used in the States. And then I spent more time giving details on OASIS3-MCT, which is one representative of the coupler approach. And we even saw that extending the functionality of OASIS3-MCT, so for example, to allow coupling between sequential coupling component running within one single executable, one single executable, then the OASIS coupler gets some characteristics of the integrated coupling framework approach. So in practice, the difference between those two categories is not that well clean cut, but you know, it still helps to have those categories in our mind, so to understand the basic philosophy of the different software. And then I presented what is new in OASIS3-MCT 5.0. So I will not go back on this, but you can ask more questions if you wish. And then as perspective and conclusion, we think that OASIS3-MCT is certainly, will most likely provide still a satisfactory solution for fully parallel coupling in our climate model for the resolutions that are targeted for, let's say, about the next 5 years. We don't think that OASIS3-MCT will disappear very fast, but still we have to plan for the next computing architectures. Something that we might be working on this year is the support of grids with masks that evolve in time, because this would be interesting for some components. So we're not talking about fully dynamic grids. The grid of the model do not change, but the mask will change, and this has some application, for example, for ice sheet models. And then we are looking also at the work done with XIOS, because the XIOS server, which is developed at IPSL, now has some coupling functionality. And we are looking at what they do. And we think that within the French community, the plan will certainly not to develop two different tools doing the same thing, but we would merge the tools and we would merge also the efforts. So we're not there yet, but we are looking into this. So I'm done. And